Good evening, everyone. My name is Sathish Kumar from Electrical and Electronics Engineering Department. Now, I am going to teach principle and operation of single phase transformer. This is the working principle of a transformer. The basic principle of transformer is mutual induction. So, means that basic principle of transformer is works on the principle of Faraday's law of electromagnetic induction or mutual induction in between the two coils. Means, according to the Faraday's law of electromagnetic induction, whenever a current carrying conductor is placed on the coil, so then induced EMF will be produced. So that induced EMF is either dynamically induced EMF or statically induced EMF. So the transformer depends on the mutual induction or Faraday's law of electromagnetic induction. In this case, the induced EMF is statically induced EMF. It means the conductor is constant, the magnetic field will be rotated. Means the interaction between this magnetic field and the conductor, then we are getting the induced EMF. That induced EMF I am calling as a statically induced EMF. So, the transformer consisting of two separate windings are there that over laminated each other. That laminated is by using the silicon steel. The winding to which AC supply is connected is called as a primary winding, and the winding which is connected to the load, that is called as a secondary winding according to this figure. You can observe here. So in this figure, it works on the alternating current only, because an alternating flux is required for the mutual induction between these two windings, that is the primary winding and as well as the secondary winding. Means, according to the Faraday's law of electromagnetic induction or mutual induction, here I am giving the primary winding is connected to the supply, secondary winding is connected to the load. So then if you are giving the supply, alternating supply to this primary winding, then flux, this coil or this conductor carries the current, then this conductor will be excited, then the flux will be produced in this coil around the clockwise direction. So this flux will be linked with this secondary winding, and then due to this linking of this secondary winding flux, we are getting the induced EMF, that is E2, and due to this induced EMF E2, we are getting the current I2. That current I2 is linked with the primary winding. So means due to the secondary winding current, I am getting the secondary winding flux Phi2. The secondary winding flux Phi2 is linked with the primary winding coil. Then again I am getting the induced EMF here, that is E1. So means this all process is called as a mutual induction. According to the mutual induction only, we are getting the induced EMF in the secondary winding, induced EMF in the primary winding. So, when the AC supply is given to the primary winding with a voltage of V1, an alternating flux will be set up in the core of the transformer. That means that links with the secondary winding, and as a result of it, an EMF will be induced in the secondary winding. That is called as a mutual induced EMF. So means this induced EMF direction is always opposite to the supply voltage V1. So this is because of Lenz's law according to this figure. So you can observe here, E1 is equal to E directly proportional to the d pi by dt according to the Faraday's law of electromagnetic induction. That is, E1 is equal to minus N1 into d pi by dt. So means whatever the induced EMF is produced in the secondary winding, or this secondary winding flux will be opposes the primary winding induced EMF E1, or primary winding supply voltage V1, according to this is Lenz's law. Okay, so then here physically there is no electrical connection between the primary winding to the secondary winding. So that's why here the primary winding and as well as the secondary winding of the transformer is connected is magnetically. That's why the transformer is the magnetically coupled, and again the power will be transferred from the primary winding to the secondary winding. Okay, so means there is no connection in between the primary winding and secondary winding. So but the power will be transferred from the primary winding to the secondary winding. So that means the transformer windings are magnetically connected and the electrically separated. So this induced EMF in the primary and secondary winding depends upon the rate of change of flux linkage in the primary winding coil and flux linkage in the secondary winding coil, that is N into d pi by dt, where N is the number of turns for if you are taking for primary winding, that is N1, if you are taking for the secondary winding, that is N2. That is, you can observe here in this place, d pi by dt, here flux linkages is the changes of the flux and also is the same for both primary as well as the secondary winding. But the induced EMF even in the primary winding is proportional to the number of turns N1 of the primary winding, that is E1 is directly proportional to the N1. Similarly, the induced EMF in the secondary winding is proportional to the number of turns on the secondary side, that is E2 is directly proportional to the N2. E2 is directly proportional to the N2. This is according to the mutual induction only. So, as discussed here, the transformer works on AC supply here and it cannot works on the DC supply. So, that's why the transformer, if you are connecting on DC supply, then what will be happen? That will discuss now. So, if the rated DC voltage applied across the primary winding, then what will happen? Then we are getting the constant magnetic flux will be set up in the core of the transformer. Hence, there will not be any self-induced EMF generation and also any linkage of the flux with the secondary winding, because we are getting the what? Here set up in the core of the transformer is constant magnetic flux, constant magnitude flux. So due to this case, we are getting we are not getting any self-induced EMF generation and there is no linkage of the flux with the secondary winding also. Therefore, there must be an alternating flux is required and also not a constant flux, because of we need to link with the secondary winding. Then only the induced EMF will be getting in the secondary winding according to the mutual induction. So if you are connecting the DC supply to the primary winding, what will happen? There is no linkage of the flux with the secondary winding and also there will not be any self-induced EMF generation here. So that's why we need to must be an alternating flux is required here. So then the primary current will be is equal to DC applied voltage divided by resistance of the primary winding if you are connecting a DC supply to the primary winding. So then the resistance of the primary winding is very low and the primary current is high, then what will happen? The current is much higher than the rated full load primary winding current. So due to this reason, the amount of heat produced will be greater and therefore there is eddy current losses will be more. So because of this, the insulation of the primary winding will be get burnt and the transformer will be damaged if you are connecting the DC supply to the transformer. Because the primary winding current will be is equal to DC applied voltage by resistance of the primary winding. If the resistance of the primary winding is very low, the primary winding current will be high. So due to of this current high, then what will happen? The primary winding current will be high and the heat produced in the winding will be more and the eddy current losses will be more, and because of that one, the insulation of the primary winding will be damages. So due to this reason, we are not connecting the DC supply to the transformer. We are connecting the only alternating supply to the transformer only. So that's why the transformer works on the only AC supply, not DC supply. Okay. So according to the principle, it is defined as the ratio of primary to the secondary turns. That is called as a turns ratio. This is called as a turns ratio. The turns ratio of the transformer is defined as the ratio of primary to the secondary turns, and if the secondary winding turns is greater than the N1, means primary winding turns, the transformer is called as a step up transformer. So if the secondary winding turns is less than the primary winding turns, then the transformer is called step down transformer. The transformer is called step down transformer. So then similarly, this is for turns ratio. That is, turns ratio is the ratio of primary to the secondary turns, that is N2 by N1. Okay. Or transformation ratio. The transformation ratio is defined as the ratio of the secondary voltage to the primary voltage. That is the ratio of the secondary voltage to the primary voltage, means it is denoted by, that is K. It is denoted by K, as E2 is directly proportional to the N2 according to the mutual induction, and E1 is directly proportional to the N1 according to the mutual induction. So then the transformation ratio K is equal to E2 by E1 is equal to N2 by N1. So this is the transformation ratio K according to the transformer principle. Okay. So now transformer will be works as an ideal transformer or as a practical transformer. So means, what is mean by ideal transformer here? Next, ideal transformer. Here the definition of the ideal transformer is the transformer which is free from all types of losses. That is known as a ideal transformer. Means it is an imaginary transformer which has no core losses or ohmic resistance and no leakage flux, and the ideal transformer has the following important characteristics here. That is, the resistance of their primary and secondary windings becomes zero, or the core of the ideal transformer has infinite permeability. The infinite permeable means having the less magnetizing current required for magnetizing their core. And also the ideal transformer has 100% efficiency, that is, the transformer is free from all types of losses. That means hysteresis losses or eddy current losses. Okay. So then next here, this is about ideal transformer. Okay, definition. So here we are getting the mainly the transformer principle is mainly depends on flux as well as the what? Turns. So then what is mean by magnetic leakage flux here? So in a transformer, it is observed that all the flux linked with the primary winding does not get linked with the secondary winding also. Okay, if you are observed, what I am saying here, all the flux linked with the primary winding does not get linked with the secondary winding also. So means a small part of the flux completes its path through air rather than the core. So, and this small part of the flux is called as a leakage flux, or magnetic leakage in the transformer. Okay, you can observe here as shown in this figure from at right, you can observe here. This is the leakage. Here flux, this is the main flux. This are the pi is the main flux. This main flux is linked with the primary winding as well as the what? Secondary winding. Okay, but some flux will be not linked with the secondary winding as well as this flux is not linked with the primary winding. Some flux will be leakage here there. So this flux I am calling as a what? I am calling here leakage flux I am calling, or magnetic leakage flux I am calling. This is the magnetic leakage flux or leakage flux I am calling. Okay. So then this leakage flux does not link with both the windings, either primary winding or as well as what the secondary winding. So hence it does not contribute the transfer the energy from primary to the secondary winding, but it produces the self-induced EMF in each winding. So means the transformer will principle on what? Mutual induction. Okay. So this leakage flux will be produces the self-induced EMF in the primary winding as well as the what? Secondary winding. Since this leakage flux will be produces an effect equivalent to an inductive coil in series with the each winding. And due to this, there will be a leakage reactance will be there. So means this according to the principle, we are getting the magnetic leakage flux in the transformer. So what is my magnetic leakage flux here? The all flux is not linked with the primary winding, or the primary winding flux will not linked with the secondary winding, or secondary winding flux not linked with the primary winding. So that type of flux I am calling is what I am calling leakage flux. This leakage flux will be affects the, due to of this leakage flux I am getting the leakage reactance in the coil, either primary winding coil or either secondary winding coil. Okay. So next, the transformer with resistance and as well as what? Leakage reactance is there in the following figure. You can observe here. The leakage reactance and the resistance of the primary winding as well as the secondary winding are here representing as a practical transformer. So this is the main practical transformer. So this practical transformer having the resistance, leakage resistance R1 and the leakage reactance X1 is there here. And leakage, this is for the primary winding, this is for the secondary winding, where R1 and R2 is the resistance of primary and secondary winding respectively, and this X1 and X2 is the leakage reactance of primary and secondary winding respectively, and Z1 and Z2 is equal to primary impedance and as well as the secondary impedance respectively. So then Z1 is equal to representation in the rectangular form will be is equal to what? R1 plus J into X1. Z2 is equal to R2 plus J into X2. So then the impedance in each winding lead to some voltage drop in the winding, either primary or either secondary. So considering this voltage drop, the equation of the transformer can be given as V1 is equal to E1 plus I1 into R1 plus J into X1. This is for primary side. And V2 is equal to E2 minus I2 into R2 plus J into X2. This is for secondary side, where V1 is the supply voltage of the primary winding and V2 is the terminal voltage of the secondary winding, and E1 and E2 is equal to induced EMF in primary and secondary winding respectively. Okay, so and also we are getting leakage reactance. This is about leakage resistance and leakage reactance, and also we are getting the resistance and reactance of the transformer here. The resistance of the transformer is defined as the internal resistance of both primary as well as what secondary winding. So in an actual transformer, the primary and secondary windings have some resistances represented by capital R1 and capital R2, and this reactances are by represented by x1 and x2. So let K be the transformation ratio. What is the transformation ratio? K is equal to N2 by N1 is equal to E2 by E1. So according to the principle, we are getting this one. Okay. So now let K be the transformation ratio. To make the calculation easy, the resistances and reactances can be transferred to either primary side or transfer to either secondary side by using this transformation ratio K. Okay. So now to make the calculation easy, the resistances and reactances can be transferred to either side. That means either all the primary are referred to the secondary side or all the secondary terms are referred to the primary side. So this resistive and reactive drops in the primary and secondary sides are representing is like this. That is, resistive drop in the secondary side is equal to I2 into R2, and reactive drop in the secondary side is equal to I2 into X2, and resistive drop in the primary side is equal to I1 into R1, and reactive drop in the primary side is equal to I1 into X1. Okay. So now according to this thing, we are getting the equivalent circuit of the transformer. So the equivalent circuit diagram of any device can be quite helpful in the predetermination of behavior of the device under various conditions of the operation. So it is simply that the circuit representation of equation describing the performance of the device is called as a equivalent circuit of the transformer. So this is the equivalent circuit of the transformer. So this is for primary winding side and this is for secondary winding side. Okay. So primary winding side, I am getting the current I1 is equal to I0 plus I2 dash. Okay. Now, so why I am getting this I2 dash and I0 is having the two components. That is, according to the principle, I am getting the working component as well as what? Magnetizing component. Okay. So this is the equivalent circuit of the transformer. Let this equivalent circuit of the transformer having the transformation ratio, that is K is equal to E2 by E1. The secondary current I2 is equal to I1 dash by K is equal to I1 dash is equal to I1 minus I0 by K. So this is about the according to the principle we are writing this equivalent transformer. We'll discuss later what is the each equation in case of the equivalent circuit of the transformer.
Like, share and subscribe. Hit the bell icon for more updates.